Hi everyone, I am Mr. Prabhu R, mathematics teacher in Kumudoti Residential Central School, Shikaripura. Today I am continuing the chapter real number, in which the theorem number 1.3 and its problems. So in the theorem number 1.3, it's basically from the fundamental theorem of arithmetic, that in the previous class I already discussed the fundamental theorem of arithmetic. What it says, every prime numbers can be factorized because of the composite number. That is, if every composite number can be expressed in the form of prime factors, so there exists uniqueness apart from the order in which the prime factors occur. So this is the statement of the previous theorem. Now it is 1.3. So what it says, statement, first of all, write down the statement. Let P be any prime number. Let P be any prime number. Then P divides a square. Then P divides a square. Automatically also P divides a. Where a is positive integer. A is positive integer. So this is the statement. Once again, that P in prime number in which P divides a square, then P divides a square and also P divides a. If P divides a square means P also divides a. So where a is positive integer. This is our statement. Now let us take down the proof. So already we know that a is any positive, some other positive integer. So that is why let prime factorization, the prime factorization or prime factors of a be. A means a is any positive integer. How we can write a is equal to? Consider. So using our previous theorem, that is fundamental theorem of arithmetic. So that is a is equal to P1, P2, P3 and so on so forth up to Pn. So what do you mean by this P1, P2, P3 and Pn? So up to Pn, these are all the primes, means where P1, P2, P3 and so on so forth Pn are primes, means prime numbers. So that is by ascending order. Consider, because P1 is less than P2 or equal to. Here P1 is less than or equal to P2, which is less than or equal to P3, which is less than or equal to and so on so forth up to P2. So that is conditions. Okay. Now, so also what the statement says, if P divides a square, so that's why I will make it as square. Now a square is equal to P1, P2, P3 and so on so forth Pn. So it becomes square. So that is why a square is equal to P1 square, P2 square, P3 square up to Pn square. Consider on squaring we can get this statement. Here what it says, so here says square. This if you extend it in terms of product also, answer will same. So it means a square is nothing but some other squares of the factors. That is why now we have already taken P divides a square, means a square is divided by P. Therefore P divides a square. So therefore by theorem of, that is fundamental theorem Theorem of arithmetic. Fundamental theorem of arithmetic. That is by fundamental theorem of arithmetic. So that is, we can call it as uniqueness. I already told that there exists a contradiction wherever a fundamental theorem of arithmetic says that composite number can be expressed in the form of prime factor, in which the uniqueness we needed. So wherever you factorize the number, composite number, uniqueness. So in which order apart from the order where the prime factors are occurs. So that is why by this we can say that here A means P. First consider P is any factor of this P1, P2, P3 and so on so forth Pn. Consider P is any factor of P1, P2, P3 and up to Pn, because we already taken P divides A square because of these statements, and fundamental theorem says already uniqueness, we need uniqueness. That is why P is any factor of this one or this one also. Since it is given that that is A is equal to P1, P2 and P3 and so on so forth. This is given. So therefore here A, otherwise that P divides A. P divides A square. Here we took the P divides A square here. P divides A square. That is why P is any factor of that given terms, that is the statement given over here. Otherwise it becomes P1 square, P2 square, P3 square up to Pn square. So by the uniqueness part of the fundamental theorem of arithmetic, we conclude that Pe divides A square and also Pe divides the A. So therefore this is the statement what we have to prove here. So this is one. Based on this theorem, that is theorem number 1.3, which is prescribed in our textbook, that is NCERT textbook. Based on that theorem, now let us discuss the example. How we can prove? You know that every rational number and irrational number also, their particular meaning. So here irrational number examples are, you know that square root 2, square root 3, square root 5, pi, 0.1, for example 0.10101 and so on so forth continuously, because their decimal expansion cannot end. That's why these are called irrational numbers. So and especially irrational number says that they cannot be written in the form of p by q. That is why I took the example. Prove that square root 2 is irrational. How we can prove? Let us solve. Solution. First, this is proved according to by proof of contradiction method. So that is called by contrary method. So that is let square root 2 is a rational number. Consider square root 2 is a rational number. Of course it is not a rational. We took it as a rational by assumption, by contrary method. So that is why now let A and B, assume that, otherwise assume A and B are positive integers where B is not equal to 0, because you can express them in the form of P by Q. You know that the meaning of rational one. Always all numbers can be expressed in this form, that is P by Q form, where Q is not equal to 0. The same way we can express like here, A and B can be positive wherever B is not equal to 0. So in order to get this square root 2 is a rational number. So what happened? Square root 2 it is equal to in the form of A by B. Consider where A and B are co-primes. Now these are called co-primes. It means once again we can confirm this. The A and B are positive integers. Of course, they have some common factor other than 1. Now consider, therefore A and B. This is by assumption method. A and B have common factor other than 1. Assume that. So therefore, whenever they have a common factor other than 1, automatically this common factor can be divided the other number, that is A or B, so that this number can divide this number. Automatically you can write this square root of 2 into B is equal to A by cross multiplication method. Now squaring on both sides. So on squaring you will get B square 2 is equal to A square. B square into 2 or 2B square is equal to A square. It says that 2 here, 2 divides A square. 2 divides A square. Therefore, also 2 divides A by theorem number 1.3, in which we just now we proved, okay, by assumption. So that is also 2. If 2 divides A square, then 2 divides automatically A also. Now let A is equal to 2C, because consider A is equal to 2C, because A can be divided by 2 and some integer. C is some integer. Consider any other integer. So therefore, substitute this value. So in this equation, substitute this value in this equation, or it has number 1. So on substituting A value in 1, so we get look here, 2B square is equal to, instead of A we write 2C whole square, so that is 2B square is equal to, it is 4C square. This 2 cancel, therefore B square is equal to 2C square. Therefore here B is another number. Already we proved A is divided by 2. Otherwise A square is divided by 2. Means now B square, so 2 divides B square by the theorem of 1.3, that is 2 divides B also. It means the fact says that, consider this statement both. It means where A and B, here now A and B have 2 as a common factor. 2 as a common factor. Look here, assume this one and this one statement. We conclude at least 2 as a common factor. But this contradicts to our assumption, that is A and B have not common factor, because other than 1. Of course, A, B are positive integers. Other than 1, there is no common factor. So that's why, therefore, assume here A and B have a 2 as a common factor because of these statements. But our assumption is wrong. Now contradiction arises because our assumption is wrong. What we assume, square root 2 is a rational one. But here A and B are as a common factor of 2. But here, according to our assumption, this A and B are not have a common factor other than 1. So that is why by contradiction by contradiction, our assumption is incorrect or wrong. So therefore square root 2, therefore here I want to write therefore square root 2 is not a rational. Therefore square root 2 is irrational. Square root 2 is irrational. Once again go through the example what I wrote here. Prove that square root 2 is irrational. So take consider any square root, that is 2 is rational one. Now assume that a and b are the factors, co-primes of this number. So according to that, square root 2 can be expressed in the form of e by q or a by b. So let us assume that at least common factor other than 1. Now assume. So this statement proved like this. Afterwards you can conclude one of the factor can be divided by 2 and the same another factor, that is prime factor, is divided by 2. Here by this statement we conclude 2 as a common factor, but our assumption is wrong because a and b have no common factor other than 1. So that is why by contradiction our assumption is incorrect. By contradiction our assumption is incorrect. That is why square root 2 is not a rational, it is a rational one. There are so many examples are given in the text, that is exercise 1.3. You can try to solve by seeing these examples. Thank you.